tech, talk about stuff in tech. So today we're very lucky to have with us our engineering manager, Florian, and he'll be having a Q&A with Jodie Burchell. She's a developer advocate in data science at JetBrains. You know, the people who make all your favorite software like PyCharm and editors for all those other inferior languages that aren't Python. I can't think of the names right now. She has a background in behavioral sciences, statistics, and natural processing. And Florian, well, he's just all around glamorous, and he leads the awesome Gina Now team. Just before we get started, quick announcement. We are having an event here in lovely sunny Berlin on the 20th of July, 7 p.m., the PyData Berlin event. So join us at our office, have some pizza, have some beer, make some friends, talk Gina, talk Python, or talk whatever the heck you like. All right, so I don't see Florian with us, unfortunately. It's quite a funny story. We don't have any internet at the office because there was a robbery downstairs of a jewelry store. And the burglars, did they cut the alarm wires? Did they? Heck, of course, they cut the Wi-Fi cables. I honestly think all of that jewelry they could have stolen, you know, the value is worth less than amazing productivity we have here at Gina. All those man hours, all those person hours wasted, crying shame. Real hit to the economy. Is it any wonder that euro is lower than the dollar now? Anyway, I'll stop rambling. Florian is here to save my bacon, and we shall get on with the Q&A. Florian, over to you. Okay,
So
great.
Just small explanation. The internet in office is currently not working because some people cut our wires in the basement. But
I just told the story.
Okay.
It gets better every time.
I have this Wi-Fi router and it ran out of battery, but now I'm here. Okay, let's do this. So I asked some questions right now.
Do you want to give a quick intro to yourself first? I mean, I introed you in, but it's better from the horse's mouth, so to speak.
Cool. My name is Florian. I'm working here on the Gina Now team. And the purpose of this team is to make the onboarding experience easy for Gina, because as every framework, TensorFlow or PyTorch, you are expected to learn this framework first, and then after some time, you are skilled enough to create good, in case of PyTorch and TensorFlow, good training code. But in case of Gina Now or Gina, you can create good search applications. And for Gina Now, you just provide your data, and then you can deploy your search case right away. That's the introduction of myself, or what my team is doing. And now
Jodie, do you want to introduce yourself quickly as well?
Yeah, so I think you've already given me a fairly nice introduction. I've actually only been in my role at JetBrains for about 2.5 months now, so definitely jumping into the fry pan. And I actually met Sophia and some of the other guys from Gina on my first week on the job at PyData in Berlin. So yeah, we sort of hit it off and decided that we would do this webinar. And yeah, so my background kind of is 6 years in data science. I did a PhD in psychology and also did some time in academia, which, you know, life on the other side's a bit more pleasant. But yeah, so now I'm kind of nerding out, getting into a lot of little rabbit holes that I'm interested in. And that's how I came to this talk topic.
Good stuff. All right, let's kick off those Q's and A's.
All right. So first question is, when I'm thinking about linear algebra, I always think about something very theoretic. And also I have to guess most frameworks already have it implemented, and like implementing another version of, I don't know, whatever, like solving linear equations or whatever algebra there is like not really or doesn't really make sense, because these solutions already exist. So as a developer, I can already assume these libraries exist. So why would I even have to learn about linear algebra?
Yeah, and as I said, I came from a background in psychology. I'm not a mathematician originally by training, and you'll hear more about this in the talk and why I sort of had the motivation to put this talk together. But I am fairly self-taught. And when I first learned Python, I had this huge reliance on using loops. And as I sort of learned more maths and more linear algebra, I actually realized exactly when and how vectorization would be useful to apply. Without that linear algebra background, I just didn't really have that right gap, that right sort of, understanding. I had that gap in my knowledge. But I think it also comes in handy in other ways. So when I got out of industry, when I got out of academia, the first industry I went into was natural language processing. And this was around the time that people were starting to really adopt language models like Word2Vec. And I couldn't understand what these models were doing because I just didn't have the mathematical background to understand like what a vector is, why it behaves the way it does, like what a cosine similarity is. So I think it's useful in practical terms. But I think it's also useful, if you want to kind of get in and understand under the hood how some things work. But I'm hoping what this talk will show you is there's really like 15 minutes in this talk where I'm actually covering linear algebra background. And I think you should be able to see that this tiny amount of knowledge can take you a long way.
Speaking of that 15-minute talk, I kind of screwed things up earlier by doing the Q&A first, like eating dessert before the main course. And that is just not healthy, people. So let's do the talk now. We'll consider the first Q&A a tasty little starter, and then we'll have the rest as dessert later on.
All right, then I will jump in. And so I've given a little bit of a motivation already, but today what I want to present on is vectorized operations in Python and how they can be used to speed up some common tasks we need to do in data science. So vectorized operations are often explored from the engineering perspective, but I haven't really seen many tutorials which explain the mathematics behind them. And what I want to do today is to go through some basic linear algebra that will help you understand vectorization. And I'll show you how this can convert a very inefficient piece of data science code into something much faster. And importantly, I'm going to be staying within Python. So people like me who don't know anything other than Python, you don't know any lower level languages like C, you can still get significant performance gains. So as I was saying, when I first started learning Python, I just loved looping. I just felt like it was magic. With a couple of lines of code, I could repeat an operation as many times as I liked. But when I started working with any kind of scale, I realized how slow looping can be. So I remember this one time quite distinctly. I was sitting for a few hours waiting for what I thought was a really simple operation to finish running over my whole data set. And I was thinking, there has to be a better way of doing this, but I just didn't have the background to know what it would be. And it wasn't until I completed this linear algebra unit that I was talking about that I finally understood these references I'd been seeing to NumPy vectorization. And even better, I realized how straightforward it was to apply them. So, it's one of those things I figured if I struggled with this, others might also be having problems. So I wanted to use this talk to pair together an explanation of a number of NumPy vectorized operations with their mathematical background. So in this talk, we're going to be going through an implementation of k-nearest neighbours from first principles and just iteratively improving its efficiency using tricks from NumPy. So the reason I chose k-nearest neighbours is that its core is pairwise comparisons. And from my experience in data science, these are one of the most common bottlenecks with code efficiency in data science and machine learning. So they turn up a lot in the sort of work that we do in machine learning, such as classification problems like KNN, clustering like k-means, calculation of metrics like mean squared error, and in broader problems, of course, like search when finding the nearest match to a query. And of course, at Gina, you guys would be very familiar with that. So, you know, it's unlikely that we would ever need to implement our own versions of these algorithms, but it is likely, and this has happened to me, that at some point you'll need to solve some sort of custom problem involving pairwise comparisons. And this is where knowing these optimization tricks comes in handy. So the structure of this talk, we're going to start by going over some of the basics of linear algebra, and then we're going to quickly go over how k-nearest neighbours works. We'll then start with an unoptimized implementation of KNN using loops and lists, and we're going to do a baseline to see how long it takes to run. We'll go over 4 different stages of optimization of our KNN implementation, at each stage replacing an inefficient part of the code with something faster. And then we'll end with a brief explanation of why vectorization is faster than using loops. So let's start from the beginning with some linear algebra. So the most basic unit in linear algebra is a vector. You can see here 3 examples of vectors. Basically, they're ordered sequences of values, typically real numbers. In the context of machine learning, vectors are used to represent data, and we can see that here. On the right, I have an excerpt of a data set I'll be using throughout this presentation. It's a bit of a weird data set. It basically describes the physical characteristics of pitches of beans. You know, it's a bit strange, but it has some great properties for this analysis, so I just went with it. So you can see here 2 of the columns, the major and the minor axis length, and this is for 3 different beans. And as you can see, each of these vectors represents a bean, with the first element representing the value of its major axis length, and the second representing its minor axis length. So you might be thinking, well, data sets can have more than 2 columns. Can I represent those in vectors? And the answer is yes, definitely. Vectors can have any number of elements from 1 to infinity. So here we have vectors with 3 elements, and having a look at the data set that we derived this from, we've now added this additional element here to represent the roundness of the beans image. So what do these vectors represent in terms of linear algebra? For the purposes of this talk, we can think of vectors as coordinates in an n-dimensional vector space. So to explain what this is, it's, as always, easiest to start in 2 dimensions. So here you can see a scatter plot of some beans against their value for this major and minor axis length. This scatter plot illustrates a 2-dimensional vector space, with the major axis length being the first dimension and the minor axis length being the second dimension. So each of these points represents a vector in this vector space, and you can see this with the vectors that we've already been looking at. You can see that their values clearly indicate their coordinates in this vector space. So vector spaces, just like with vectors, can be any number of dimensions. You can see here our 3-element vectors live in a 3-dimensional vector space with an added dimension for roundness. So the beans data set has 16 feature columns in total, and I can represent each bean as a 16-element vector, which lives in a 16-dimensional vector space. We obviously can't visualize that, but what I really want to emphasize from the beginning of this talk is that the principles that we apply to 2- and 3-dimensional vector spaces translate directly to vector spaces with any number of dimensions. So now that we've covered vectors, matrices are pretty easy to understand. They're simply a collection of vectors from the same vector space. So you can see here that we have 3 of our 2-dimensional vectors, and as they all belong to the same vector space, we can put them together in one matrix. Bringing this back to the dataset concept, this matrix is conceptually equivalent to our data frame containing 3 different beans with 2 different columns. So how is this represented in NumPy? NumPy uses a concept called an array to represent vectors and matrices. Arrays, confusingly and unfortunately, have their own concept of dimension, and this differs from how we've just been discussing it in the context of linear algebra. Think of it as the number of sides in which an array can change length or size. So starting with vectors, vectors are represented in a 1-dimensional array, And that's because vectors only ever change size in terms of the number of elements that they contain. So you can see that here, where vectors will always have a size of 1 in this direction, but they can change size in this direction. Arrays also have a property called shape, which tells you the size of each dimension. So for this 1D array, we have only one value in our shape tuple, which has a size of 2, representing the number of elements in the vector. Matrices are unsurprisingly represented in two-dimensional arrays. This is because we can have information about the number of vectors in the matrix and also the number of elements within each vector. So this 2D array has a size of 2, 2, representing two vectors of size 2. And then finally, a slightly more complex concept within NumPy is that of n-dimensional arrays. This is essentially a reshaping of 1 or 2-dimensional arrays, so they sit in a higher dimensional space. So you can see here that this 2-dimensional matrix has been reshaped so that it's now a 3-dimensional object, with the first dimension representing the number of matrices, the second representing the number of vectors, and the third representing the number of elements. So we'll be coming back to 3-dimensional arrays later, so hold on to this concept. So next, I just want to go over how k-nearest neighbours works. So a useful property of vector spaces is that vectors that are close to each other tend to be similar, and those that are distant from each other tend to be dissimilar. So we can see that here in our vector space with the major and minor axis length, with those beams that are the same type, represented by the same color, sitting close to each other, and mostly those beams that are of different types being far away from each other. So there are many, many different ways of measuring distance, but the two I want to look at today are the Manhattan and the Euclidean distances. So to understand the Manhattan distance, imagine that within a two-dimensional vector space, you can only travel along the x and y axes to get between 2 points. So in this example here, if I wanted to travel from this point here, 2, 1, to get to this point, 4, 3 here, I would need to go 2 spaces along the x-axis and then another 2 spaces along the y-axis. And then we simply add together the number of spaces we moved to get a total Manhattan distance of 4. We can, of course, get this value by instead subtracting the 2, 1 from the 4, 3 element-wise, so 4 from 2 and 3 from 1 to get a total of 4. So we can generalize this to the Manhattan distance formula, which is the sum of the absolute differences between each element of the vector. So we take the first 2 elements from each other, the second 2, all the way up to the nth. And what I want to emphasize is, again, even though I'm visualize this for vectors with 2 elements, it applies to vectors with any number of elements. To understand the Euclidean distance, imagine that we now had to find the shortest distance between these 2 points. So to do this, we can imagine that this path that we travel to get the Manhattan distance forms the 2 shortest sides of a right-hand triangle, and the Euclidean distance is the hypotenuse. So if you remember back to high school math, this might twig you to the fact that you can use the Pythagorean theorem in this 2-dimensional example to calculate the Euclidean distance. So we know that the 2 short sides of the triangle are given by 4 minus 2 and 3 minus 1. If we just work through this math, we get 2 squared plus 2 squared, so 4 plus 4, which gives us 8. So because this is d squared, we now need to take the square root of 8, and then that gives us our total Euclidean distance of 2.8. So of course, we can generalize this into a formula for any number of dimensions. And what we do is we take the square of the differences of each element, sum them together, and then take the square root, just like we did up here. So again, you can see that I'm going from 1 to n. So this applies to vectors with any number of elements. So it turns out we can actually use one formula for calculating both the Manhattan and the Euclidean distances, which is called the Minkowski distance. So the Minkowski distance takes each pair of elements in 2 vectors, takes their absolute distance, raises these to the power of p, sums them all together, and then raises the whole thing to the power of 1 over p. So for the Manhattan distance, p equals 1. You can see that because anything raised to the power of 1 just returns itself. If you get rid of these 1s, you can see that this is functionally equivalent to the Manhattan distance formula that we looked at a couple of slides ago. for the Euclidean distance, p equals 2. And again, you can see that this is functionally equivalent to this Manhattan distance formula, Euclidean distance formula that we just looked at, because we're raising it to the power of 2 here, and anything raised to an even number is even. So we don't actually need this absolute difference calculation here. And then, of course, this raising to the power of 1/2 is equivalent to taking the square root. So finally, let's go over how k-nearest neighbor works, and then we're going to get to the code, I promise. So we take a data set, and then we split it into a train and a test set. So what we need to do is we take one test point at a time, represented here by this orange dot, and we measure its pairwise distance between every single training point. So as you can see, this is a very expensive operation, especially with a large data set. Next, we sort every training point by distance, and we retain the k-nearest points to our test points. So this is where the name k-nearest neighbors comes from. So k is kind of arbitrarily chosen. It's usually a smallish number between like 3 and 10, but it's, you know, something that you tune based on your data set. What we then do is we tally up the labels of these k-nearest neighbors, and we just check what the most frequent one is. And in this case, it's obviously Cali. So we'll assign a label of Cali to this test point. And we just iterate through the entire test set until we've labeled every single test point based on the most frequent label of the nearest neighbors. Okay, so with that covered, we can now move on to creating our first implementation of the KNN algorithm. So I'm deliberately starting with an implementation that relies very heavily on lists and loops, because again, this is where I started in Python. And we're going to time how long it takes with a few different samples of data in order to get baseline times. So let's jump over to our IDE now. Obviously, I'm using a JetBrains IDE. This one's called DataSpell. And let's just go through our functions briefly. So the first function we've implemented is to calculate the Minkowski distance between two different vectors. So what you can see is I've represented these two vectors as lists here, and then this code just goes through and applies that formula that we looked at a couple of slides ago. Scrolling down here, this next function applies this Minkowski distance function pairwise to every combination of vectors between the training and the test sets. And again, I've represented those two data sets as lists, this time as lists of lists. I'm deliberately staying away from pandas because pandas has some NumPy optimizations under the hood, and I just wanted to steer clear of that. The next function is designed to find the most likely label for a single test observation based on the closest training observations. So it does this by sorting the labels from closest to furthest away to a test point. And then it calculates the most frequent label of those k-nearest neighbors. And then finally, we bundle everything up into a convenience function in order to run this code over every single test point in this loop here.
Sorry, just a small question. It was a bit too fast.
Bit fast, yeah.
Can you go up again to the code?
Yeah, which one do we want to see?
Yeah, that one. Calculate nearest neighbors, exactly. And then we have an item getter, 0, and then in brackets we ignore the first element.
Yeah, because that's
this is our element.
Yeah, okay. Exactly. Yeah. And this is just zipping together the distances between a test point and every train point, and then their class labels. So the Cali and the Dermison and the Seca that I showed a couple of slides ago.
Okay, cool. Thanks.
No worries. I wasn't sure how much detail to go in the code because there is a lot to get through in this talk, but just jump in at any point if you want me to go over anything. I'm also, I've got a repo with this code committed. So I'll share that on Twitter. I've got to update it, but I'll share it on Twitter after the talk, and then you guys can play around with it if you'd like. Cool. Okay, so now that we've gone through the implementation, let's just briefly chat about the data that we're going to be using to time this implementation. So as I said, we're going to be working with this Beans data set. The data set has a total of around 13,000 observations. And as I said, it has around 17 feature columns. It has, 16 feature columns. The 17th column is the class labels. So that's why there's 17 here. And what I've done is I've created 3 different data sets for testing. So the first I'm calling the small data set. It has 3 features and 400 observations. So 300 of those are assigned to the training data set and 100 to the test data set. The next is the medium data set. So that has the same 3 features, but this time I'm using all of the observations. So it has around 10,000 training observations and 3,500 test observations. And then I have what I'm calling the large data set. It's really just the whole data set. It uses all 16 feature columns and then all of the observations. So let's get to the good bit. Let's see how long our baseline timings took. So for our teeny tiny small data set, we took 224 milliseconds to complete the whole implementation. For our medium data set, we took 3.5 minutes. But when we get to our large data set, we jump up to 12.5 minutes. So what happened here? Well, the main difference in the time that it takes to run KNN over the medium and large samples comes from how we're calculating the distance between 2 vectors in the first function. So in order to calculate the distances, as you can see in this piece of highlighted code, we're looping over the vectors. That's what this represents here. And then we're taking the differences one by one. So as the large sample has 16 features and the medium sample has only 3, we're seeing a consequent scaling up in the computation time. As such, the first way we're going to shave off some time is getting rid of this loop. In order to understand what we're going to do, though, let's first cover some more linear algebra. So it's possible to do a number of arithmetic operations on vectors and matrices, including addition, subtraction, and multiplication. So obviously for our purposes, being able to do subtraction is very interesting. It's very simple. So the way it works is if you have 2 vectors or 2 matrices of the exact same size, you can do the subtraction operation. Pretty much what happens is the elements line up and then you get a vectoral matrix of the same size returned with these differences returned in this vectoral matrix. Works the same way as it does with vectors with matrices. You just get those elements lined up along the columns or the rows, and you get a matrix of the same size returned with those differences. Something else you can do with vectors is apply transformations to each element. So these all involve passing vectors or matrices through functions in the same way that you would with just a number, a scalar, and getting a vector or matrix of the same size in return. So examples of such functions include multiplying every element by a constant called scalar multiplication, raising every value to a power, which is called the Hadamard power, or taking the absolute value of every element. So I think you can see where I'm going with this. So I have here an example of raising each element of this vector here to the power of 2 and this matrix to the power of 3 using this Hadamard power. You can see it's nothing special going on. It's literally just squaring or cubing every element and returning a vector or matrix of the same size. So I think this gives you an idea of how we can improve this function. Let's jump back over to Dataspell and jump into our second notebook. And we're going to improve our first function here to calculate the pairwise distances between 2 vectors. So the first thing that you can probably notice is that instead of inputting the 2 vectors as lists, we're inputting them as arrays. And what that means is we can just do this vector subtraction straight up. You can see the notation is very intuitive, just like you would if you were subtracting 2 numbers. And then what we have is an array, a 1D array with the differences. We can then run this numpy abs function over the top, and that will give us the absolute differences. And then we then run this numpy power operation over the top of the whole thing. And then we can do the rest of the function as per in the previous implementation. So let's scroll down and see how much time this has shaved off. So we're down to 174 milliseconds for the small sample, around 3 minutes for the medium sample, but the best gain has come from the large sample, no surprise, where we're down to around 4 minutes. So to make this a bit more concrete, let's look at this as a function of the baseline time. So we're down to around 1.2 to 1.3 times faster for the small and medium samples, But when we hit the large sample, we're now 3.2 times faster. So this is great. We've already managed to make some pretty good performance gains with this really simple change. However, we really haven't made much of a dent in the computation time for the small and the medium samples. So the main culprit is actually this nested for loop that we're using to calculate the pairwise distances between each test observation and every train observation. A major issue with loops, as we've already gotten a taste of, is that there's sequential operations. And once we start nesting loops, the number of operations that we need to compute sequentially scales as a function of the product of the elements in each list. So we basically multiply the length of one list by the length of the other because we're permutating through every combination of each list. So this means that even with our teeny tiny small data set, we're running 30,000 sequential operations to get the distances between each list. With the medium and the large samples, we're pushed up to 35 million sequential distance calculations. So spoiler alert, this is making up a huge chunk of the time it's taking to do KNN on those larger samples. And think about it, this is actually a really small data set. When you're talking about like real machine learning data sets, you're talking hundreds of thousands, millions of observations, or even more. So using nested for loops becomes prohibitive or sometimes just intractable. So our second improvement is going to focus on our second function, and we're going to get rid of this nested for loop and replace it with something vectorized. Within the second function, we have this chunk of code here where we're creating permutations between each of the train observations and each of the test observations. So to understand how we're going to get rid of this, we're going to extend a little bit on what we've already covered about vector subtraction. And one of the coolest things I think NumPy can do actually. So to start, let's imagine that we have these three vectors here, x, y, and z, and we want to find the pairwise differences between them. So for KNN, the way we've been doing this is with the nested for loop so far. Let's start with getting the difference between each vector and the x vector. So one way we can do this more efficiently than looping is to combine all three vectors into one matrix, which we can do because they all live in the same vector space. And then we can make three copies of the x vector. And because we now have two matrices of the same size, we can just do straight vector subtraction. So all good so far. But the problem is we're going to have to loop in order to get the differences for the y and the z vectors, right? Well, the answer would be yes if we were restricted to using 2D arrays. But fortunately, as NumPy, as we've already seen, supports 3D arrays, we can actually do everything in one pass. So let's look at how this would work. So let's take our first matrix, represented here as a 2D array. So we have one copy of the x, one copy of the y, and one copy of the z vectors. So what we can do is we can reshape this into a 3D array with the shape 1, 3, 4. And then what we do is we replicate it 3 times. So we end up with a 3 by 3 by 4 3D array. We can do something similar with the matrix containing 3 copies of the x vector. We also reshape it into a 1 by 3 by 4 array. And then what we do is we take the y vector, make 3 copies and reshape that into a 1 by 3 by 4 array and do the same thing with the z vector. And then we sort of squish them together into the same array. So we end up with another 3 by 3 by 4 array. So now we can just do straightforward vector subtraction because every element lines up along every dimension. And I think you can easily see that here, x from x, y from y, y from z. So we can do everything in one pass, and it's a massive improvement over looping because we're no longer bound to that sequential processing of each difference. However, one problem you might have spotted is I'm explicitly replicating each vector 3 times within each 3D array. And this is fine when we're talking about 3 vectors, kind of. But once we start dealing with sizable data sets, we're going to be creating these massive arrays in memory, which is not very efficient, and your computer might not even be able to handle it. So NumPy luckily has another trick to help us out here, which is called broadcasting. Broadcasting is super cool. So it's essentially a memory efficient way for NumPy to do the sort of operation we just did without the need for explicit replication of the vectors within the array. So the way that it works is that if we want an operation with two arrays, or we want to do an operation with two arrays, NumPy will first compare them and check if they have the same number of dimensions. So are they both 2D arrays? Are they both 3D arrays? If so, it will then check whether the arrays have the same size in all the dimensions. If so, then great. The operation can just be carried out directly as the elements all line up, just like in our previous slide. However, if not, it will do one other check. It will check whether one of the arrays has a size of 1 for that dimension. If that's the case, then it replicates the array along this dimension of size 1 until it's the same size as the other array's dimension size. Sort of like what we just explicitly did, but it's a bit confusing, so I'll show you how it would work with our small example. So to start, let's take our original matrix with one copy of each of the vectors, again represented as a 2D array. So to get the first array for our subtraction operation, we reshape this 2D array into a 3D array again. And we're doing the same thing we did before. So we have one copy of the matrix sitting in the first dimension. So a 1 by 3 by 4 array. So to get this second array for our operation, we do something slightly different. We take our same 2D array, but this time we reshape it into a 3D array. So we have this one copy of the matrix sitting in the second dimension. So a 3 by 1 by 4 array. So what happens when we try to subtract one of these arrays from the other? Well, NumPy matches up each dimension and it checks the size of each. In the third dimension, we're sweet. They're both size 4, so nothing needs to be changed here. However, when it checks the first and the second dimensions, it sees that the sizes don't match. So because it can see in this first array that this one's a size 1 and this one's a size 3, it knows that it needs to stretch this array along the first dimension in order to match the size of the array that we want to subtract from. Similarly, with this array, it can see because we've got a size of 1 in the second dimension, it needs to stretch along this dimension in order to match the size. Then it can do, basically has an implicit representation of what we just did explicitly. And when the subtraction operation is finished, it will return a 3 by 3 by 4 array containing all of the element-wise differences. So thank you, NumPy. So let's jump over it and see how we can implement this. So we have our third notebook, and what you can see is some pretty big changes. Instead of having separate functions to calculate and apply the Minkowski distance, we have one single function. And what it now intakes is all of the test observations and all of the train observations represented as 2D arrays. What we then do is we do our broadcasted subtraction. So we need to reshape these 2D arrays into 3D arrays. We use this slicing notation. I'm not going to get into it too much. We can kind of revisit it at the end of the talk if you like. But essentially this none notifier says that we want to set this dimension to 1. So this is the first dimension, this is the second, this is the third. So we set this dimension to 1, we set the second dimension to 1 in the second, and because we have this dimension matching size, because it represents the number of features, we can essentially do this broadcast operation. What we now have is, again, a 3D array containing all of our element-wise differences. And because it's just an array, we can do the same element-wise method application that we did in the last implementation of this function, because it's just an array. We had a 1D array last time, now we have a 3D array. And then we can similarly, right at the end, sum along all of the features and raise everything in this final 2D array to the power of 1 over p. So let's see what this gained us in terms of time. So for the small data set, we're now down to around 20 milliseconds. For the medium, we're down to 23 seconds. And for the small, we're down to 40 seconds. So comparing this to baseline, we're now 9 times faster for the medium, 11 times faster for the small, and a stonking 11 times faster for the large data set. But there's still more we can do. So the next thing we're going to do is have a look at how we've implemented the distance measurements. So we've created one formula for Minkowski distance, but for the purposes of our KNN implementation, we're never working with anything other than the Manhattan and the Euclidean distances. So you might have been thinking when I was talking about the Minkowski distance functions that there's actually quite a lot of redundant calculations that are done. So for the Manhattan distance, we're raising things to the power of 1, and that doesn't actually change the values. So for the Manhattan distance, we have 2 points where we raise all of the elements in these arrays to the power of 1, and we don't actually need to do that. Similarly, with the Euclidean distance, we're applying an absolute value function and then squaring everything. But if you square things, they're always even. So you don't actually need to apply that absolute value function first. And the reason we should care about this is even though these NumPy functions are written in nice, efficient C code under the hood, they're still using loops. And so the longer that your arrays get, the more time it takes to apply these. So in our particular case, it actually makes sense to split the Minkowski distance function back into dedicated Manhattan and Euclidean distance functions just to get rid of these unnecessary methods and shave off a bit more time. So we're going to revisit our brand spanking new Minkowski distance function. And this time we're going to be dealing with these 2 lines. So we're going to be getting rid of the redundant functions and doing this in 2 separate dedicated functions. So going back to data spell, we can see in our 4th notebook, we now have this dedicated Manhattan distance function. It's basically the exact same code. We're taking in these 2D arrays with the test and train observations and doing our broadcasted differences. But this time you can see that I've gotten rid of those 2 redundant power calculations. Similarly, with the Euclidean distance, we have the same first part, but we've gotten rid of that unnecessary absolute difference function. So let's see what effect this had on our times. So for the small data set, we're down to around 15 milliseconds. For the medium, we're down to around 20 seconds. And for the large, we're down to 32 seconds. So again, having a look at this as a function of baseline, we're 11 times faster with the medium, 15 times faster with the small, and 24 times faster with the large data set. And again, the larger data set had those greater gains because it's 16 features rather than 3. Okay, so we're on the home stretch. We've now done a few important changes to our calculation of the distance metrics. And this has already improved our time to implement KNN up to 24 times, as we've seen. But we haven't touched the code to implement KNN itself. And this is all still entirely written in lists. So our final improvement will therefore focus on gaining some speed here. So to refresh your memory, the code for calculating the neighbor of each test point sorts these list of distances from the test point to each training point. And there are 2 expensive operations here. The first, as we've already talked about a little bit, is this sorting, where we have to sort the entire training data set for every single test point. This is followed by this list comprehension here, where we again iterate over every observation in the training set in order to just keep the label from this zipped list here. So why is there a problem with this code? Or there are 2 problems. The first is with the sorting algorithm that's used in lists. Sorting in lists, I did a bit of digging, and it's actually locked into one specific sorting algorithm, timsort, which is efficient, but may not always be the fastest sorting algorithm that could be used. In contrast, NumPy sort and argsort both have a bit more flexibility. So for example, when you don't specify whether you want a stable sorting algorithm, NumPy sorting will default to the faster quicksort. And even when you choose stable sorting, the algorithm will be adjusted to the data type of the array. And then the second issue is this sneaky list comprehension that we have. So list comprehensions, as we know, are for loops by another name. So this is likely causing another bottleneck because, again, we have that sequential processing. So let's jump over to looking at our final bit of code. So skipping down to here, the first difference that you can probably see is that, again, we've moved over to arrays rather than dealing with lists. So now we've represented the distances and the labels as arrays rather than lists. we can now take advantage of using NumPy's more flexible sorting algorithms, which is going to be a bit faster than using timsort over the list. Secondly, and probably more importantly, because this whole thing is represented as a 2D array, rather than needing to loop over every element to extract those labels, we can actually just use indexing, where we tell NumPy, I just want to keep this column. So let's go and see how we got with our final timings. So for the small data set, we're down to around 12 milliseconds. With the medium data set, we're down to 7 seconds. And with the large data set, we're down to 20 seconds. So our final timings, we managed to get 19 times faster for the small data set, 30 times faster for the medium data set, and for the large data set, almost 40 times faster. So these are quite impressive gains, but what I want to emphasize is this is quite typical from what I've seen when I've looked around at blog posts or tutorials or anything else explaining these vectorized operations. So what I've done here is nothing special compared to what you'll be able to implement in your own code and the sort of gains you can expect for your own optimizations. So let's just quickly cap out by very briefly talking about why it's faster to use arrays rather than lists. So this is going to be a very high level explanation, but I think it's sufficient to get an idea of what's going on and where this speed is coming from. So let's say we're working in a Jupyter notebook and we've created this variable here, A. So that variable will live in memory at an address. And let's say we create another variable, C. So that variable also have its own address in memory. But as you can see in this very simplified illustration, these memory addresses may not be sequential. In fact, they may not even be close to each other. So the thing is, because memory is massive, it's divided into blocks called pages. You can kind of think of pages like postcodes in the UK. I don't know if you're familiar with them. My sister lives in the UK and they have these postcodes that refer to like small numbers of addresses. So for my sister, her postcode includes her house and like 5 of her neighbours. So the page division obviously makes memory easier to work with in the same way that these UK postcodes make it much more efficient for Royal Mail to deliver letters. The thing is that the CPU is really lazy and it won't do operations with variables unless they're physically close to it. So this means that if I wanted to do an operation with A, the entire page that it's located on will be physically moved right next to the CPU so that the operation can be completed. So this is akin to if the post office needed to move my sister's house and all of her neighbors right next to the post office just to deliver a letter. So how does this work with lists? So let's say I create this Python list with 5 elements. And what I would have expected, like before I started reading about this, is that, the elements of those lists would be stored kind of close to each other, but they're not. They're stored in separate addresses in memory. And you can see that they may not even be on the same page. They may be scattered quite far away from each other. So let's take this extreme case where every single element ends up on a separate page. What happens when I try to loop over this list? You get this happening. As you can see, for each element, the entire page needed to be moved to the location next to the CPU. Each page is around 4 kilobytes, which means that for every element in the list, 4 kilobytes of memory is being moved. And as you can imagine, this is the main thing that makes looping over a list so slow. In addition, there are a few other things that make it slow. Lists allow mixed data types, which means the interpreter has to check the data type of each element before running the operation. And this involves doing a number of checks, including even seeing whether the operation that you want to perform on the element is valid. In contrast, let's say I create this NumPy array here. Each element in this array will be stored next to each other in a contiguous block of memory. Now, there's a good chance that the elements of my array are going to be spread over just a few pages. And this is going to cut down on the number of pages that need to be moved to run my operation over the whole thing. Moreover, as arrays are locked to a single data type, this makes it easy to subset the array using index. And it also means the interpreter knows the data type of each element in advance, so it doesn't have to do those additional checks that it would with list elements. And finally, certain NumPy operations can be parallelized using a type of processing called SIMD, or single instruction multiple data. And this means that the data within an array can be broken into blocks. Say we have this 2D array here, and both of them can be processed at the same time. So this gives us another speed boost compared to the entirely sequential processing that loops lock us into. So let's do a summary of what we covered. So our first optimization involved doing vector subtraction between two one-dimensional arrays rather than looping over each element. This actually got us some pretty significant speed boost for a very simple change, got us up to around 3.2 times faster than baseline. We then extended vector subtraction using 3D arrays and broadcasting instead of using a nested for loop, and this got us up to around 19 times faster. We then removed some redundant element-wise operations by splitting our Minkowski distance function into separate Manhattan and Euclidean distance functions, and this saved us some time as NumPy loops over arrays under the hoods to apply these functions. This got us up to around 24 times faster. And then finally, we moved our KNN implementation from list NumPy arrays, benefiting from both the more flexible sorting methods implemented in NumPy and removing an additional list comprehension by using indexing. And this got us up to our final time gain of up to 38 times faster than baseline. So thank you. I hope this gave you a good grounding on why NumPy's vectorized operations work the way they do and when and where it can be helpful to apply them. And here are my details. My Twitter handle is here. I tweet pretty regularly about what I'm working on in data science. And as I said, I'll share that repo with the notebooks. And I also run a blog. I actually have a series covering some of the content in this talk. So please feel free to visit to get some more details.
Really cool. Thank you.
No worries. Thank you for your engagement.
Yeah. So I think it's really underestimated how much you can gain if you really understand what the library is doing. And
yes.
Yeah, so like my question I had there in the beginning is kind of answered by this talk, because yeah, you understand how NumPy works, and therefore you know you should not loop over everything, but just use the vector operations and all these kind of optimizations. So it helps to, as you said, to optimize by a certain factor. So what was it, like 33 times faster, which is incredible. And if you can save, so for a company, you go there, you implement for them, and you can save that much of computation costs for them, they will be very happy, I guess.
Yeah.
So,
yes.
so
not a few hours. Yeah. You go.
Exactly. So my question would still be, when thinking about runtime complexity, NumPy should do under the hood something similar to looping. I mean, something more complex, maybe some, but it's still a quadratic operation, right? And we scale up the data set, then this quadratic nature would kick in at some point, and it will become again quite slow. There's some, so we at Gina, we use approximate nearest neighbor, we're trading off a bit of accuracy.
Yeah.
But, yeah. So I would like to get your perception on this. And
yeah, this is actually a really interesting point. So I actually came, like one of the problems I had to solve in terms of pairwise vector operation, was it was a couple of jobs ago, and I was working actually in a search engine, doing a lot of NLP stuff. And basically we wanted to incorporate semantic search. So we had, it was pretty simple. We created word-to-vec models, and we essentially wanted to find the closest skills to job titles or vice versa by searching the vector space. So like when you've got like a few million different vectors, it's not fast, and you're trying to do this at search time. So at that point, I don't think you really have a choice but to start getting to approximate methods. I was actually doing a bit of reading, and KNN and sklearn actually doesn't calculate every single neighbor. They do approximations as well. And that's, I think, like, it's so expensive. I don't think you can really justify it. So that's when you need to, start approximating as much as possible.
Okay. And, do you know some algebra stuff on how to do this?
So I actually wanted to put it in this talk, but there was already so much. I couldn't cram it in. So the way that we did it, we actually did it in Java, but there's a algorithm called Tarsos LSH. So it's locality sensitive hashing. And the idea is, it's a little bit technical, but basically you have like 100 dimension vectors. And what you can do is you can actually like reduce them down to a single number by, like, it's called projection. So you basically just approximate where they would live on a much smaller vector space, just a line. And then what you can do is, because, you know, they're like, these numbers mean something about how similar they are to each other, you can sort them and then divide them into hash bins. And then you just search within that hash bin, and that gives you a much smaller search space. And because, again, you're doing an approximation, when you convert it from like 100 to one number, you can like do this multiple times and then compare across the hash bins and be like, okay, if it's in this hash bin like 3 times out of 5, then it's probably fine. You know, these are probably the right neighbors. Yeah, it's really interesting. I've got a paper about it. I'll post it on my Twitter as well.
Okay, cool. I will check it out.
Did you have another question for me, or should I shoot
Maybe,
for you?
Maybe we look at the audience. Are there any questions so far?
Okay, we've got one question from Jake. Thanks for the question, Jake. Which LHS did you use?
Yeah, so sorry, it's called Tarsos LSH. Wait, I can actually even just Google it right now. Tarsos LSH. So this one here. So yeah, you can see that this was the implementation that we used on Java. So if you are a Java coder, you can have a look at that. There's also, like, this was a few years ago, I think things have moved on, but there's other hashing algorithms, of course, that you can use. So it's another one called approximate nearest neighbors. Oh yeah, annoy. I think that one's entirely in Python. There's also like for doing private, like privatized grouping of people into audiences in the browser, Google was using one called Flock, which is another type of hashing, which, you know, creates, you know, anonymization of data in order to, yeah, like there's all sorts of hashing algorithms. So yeah. Maybe I'll fire a question at you, Florian.
Okay.
So yeah, so obviously having done search stuff myself before, like, it's such an interesting area. And I'm actually curious about how you guys handle the amount of scale you'd have to deal with unstructured data, because it's a very heavy process.
So basically, as I said, Gene is a framework which allows you to write your search application on a very high level, end to end, like giving the full experience. And all these individual components which are used for new research. So this might be certain machine learning model or an indexer. They can be swapped as wanted. So we support, basically, by this framework, we support all kind of indexers, other companies create, because there's always possible to use our framework to create an executor which makes the connection to that indexer, to that vector database. But we also have our own development of indexers, which are currently used for like mid-sized data sets. So we can, like, even ourselves with our own in-house indexer, we can go quite far. We also we have sharding and replicas. We support to have like redundancy. What happens if one pod fails because cluster grows and at some point there's not enough nodes to schedule all the pods, then Kubernetes will just let one pod fail. And if this is part of the index, like usually data would be lost, but since we have replication, then you can just, you still have your data on that indexer. So that's basically the answer. Or is this question answered?
Yes, definitely. And it's interesting too, because I was really just asking from like a data scientist perspective, like how do you scale? But you're obviously talking about implementation issues as well, because you can't scale something like this without redundancy because nodes do fail. Servers die. So yeah, it's even more complex because you're dealing with replication.
Yeah, that's true. We face all the issues like everyone would face when they create their own neural search. And actually, when working in my previous companies, all over again, I went through the process of building a neural search. And so I'm quite happy working here, like solving this problem probably once, and then this solution can be applied to a lot of search tasks.
Yeah, it's super cool as well. So I've been digging a bit into the stuff about transformer models at the moment, which is obviously like the stuff that everyone's super interested in. And I think like the representation of objects as neural nets, like as vectors, is like it is where we're going. Like I think we're moving away from structured data because it's so expensive to produce. It doesn't tend to have scale, and moving into like, how do we efficiently handle unstructured data?
Yeah, I agree. So for instance, we work with online shops together, and then usually it's not just one online shop. They have their item feeds from a lot of different aggregators, it's called, where they collect the item feeds from like 500 different shops, which all have clean data, but it's like a different format and everyone has their different. So like even combining clean data makes the data dirty. So
yes,
I fully agree on your point.
Yes.
And yeah, by the way, if someone from the attendees is also interested in a new search case, especially in e-commerce, product search or something, you can just reach out to us. We're currently putting quite some effort in optimizing for this case.
Yep. If you're not already on our Slack, hit up slack.junior.ai and you can talk to us there.
So any other questions from the audience?
Don't be shy.
Or if you're shy, just write.
Yeah, if you're shy, write in the Slack or write to me on Twitter later. Also fine.
I'm not seeing any more from the audience. They're very shy today. Should I start calling on people like
no.
No, I'm not.
Don't be a bully.
Let's do it once. Okay. All right. No.
I'm just looking for someone who works at Gina so I can pick on them without recriminations. But no, I'll be nice. All right. So I guess that's a wrap. So yeah, Jodie, thank you so much for being here with us today. Everybody be sure to follow her on Twitter. And yeah, if you have any questions, follow-up questions, ping us on Slack or ping Jodie on Twitter. And yeah, don't forget, if you're in Berlin, don't forget to come to our PyData meetup next week on, let me bring up the date, the 20th of July. That is What day is the 20th of July? That is next Wednesday. So yeah, we're looking forward to seeing you all. As always, chat to us on Slack at slack.gina.ai. And yeah, we'll see you at the next Engineering All Hands a month from now. Stay tuned to meetup.com. Thanks, everyone.